You have the exact prime number, the nth prime number. And starting to think about the next best thing, you know, the prime counting function, which we denote by pi of n or pi of x. This has nothing to do with the number pi. It's an unfortunate choice, or you know, but
no pi from prime.
no prime. Yeah, pi from like p. You know,
P in Greek.
yeah, p in Greek, exactly. But I mean, it has nothing to do with the number pi.
It's 3.14.
Yeah. But whatever. So, and this prime counting function is just the number of primes less than or equal to n. So pi of 10 is 4 because the only prime numbers less than 10 are 2, 3, 5, and 7. For example, same thing for pi of 100. For example, pi of 100 would be 25 because there's exactly 25 primes under 100. For example, we go here, we see the 25th prime is 97. So the 25th prime is 97. So pi of 97 would be 25. Pi of 98 would also be 25. And so forth. 99, 100, eventually till you get to pi of 101, which would jump up to 26. Because 101 is now the 26th prime. It's the next prime after this guy. So back to formula for, the prime counting function. So this is Gauss and Legendre noticed this more or less empirically. Gauss just had an amazing intuition for this, but it was more or less an empirical observation. They just said, oh, look, this. No, well, first they started considering this problem, and then they. Alright, yeah. This is just a percentage. You see, there's 25 primes under 100, so the percentage is 25. 1 in 4 numbers are prime under 100. And it keeps going down. You see how the percentages go down? If for example, if here, 16.8, if this stayed constant from then on, if 16.8% of numbers stayed constant as prime numbers, by the time you get down here, this number would be 168. 168, whatever billion that is. And this would be also 16. This would also be 16.8. But as you can see, the density of the primes, it starts decreasing, and it actually approaches 0. But how we saw in Euclid's theorem, they never really run out, ever. But the density approaches 0. Eventually, we go big enough into these numbers, this percentage, the number of primes, would approach 0, but we'll never still run out of prime numbers. So, yeah, so this is where we're really going to start our study. It's this prime counting function because remember that P of n, that just finding the nth prime is literally just way too hard. And so what I was trying to make here, pi of x, the prime counting function, is a step function. It stays constant until you hit that prime and it jumps up 1. And then it stays constant until you hit that prime and it jumps up 1. So it's a step function. It's just the amount of primes less than or equal to n.
But the shape of these graphs suggests
yeah, very suggestive it does for you to consider a logarithm. So in the last decade of the 18th century, 15-year-old Gauss and Adrien Marie Legendre both discovered an approximate formula for pi of n or pi of x. More or less, it's x over log of x. It gives you a very good estimate. So for 100, the amount of primes is 25. 25 over log of 25, where log is understood to be natural log. This is number 3. We don't use nothing else for natural log. 21 point whatever. This is the difference. Same thing. You could read the numbers yourself.
And please give us the graph of the previous slide.
Sorry?
The graph of the step function. It looks like the graph if you...
Oh no, we're gonna see watch, we're gonna right after this, we have like one more slide to see the nice graphs with everybody. So it's just so here's pi of x, here's x over log of x, n over log of n. Here's their difference. This is your error. And as you can see, and the prime number theorem, even though this error here looks pretty big, you're off by this many primes by the time you're considering numbers this big. But still, the prime number theorem the prime number theorem, which I don't have time to talk about like in depth, it's this statement that the limit as n approaches infinity of pi of n over n log of n. As you take n to infinity, they asymptotically approach 1. What's it called? So this is the prime number theorem. And so the prime number theorem, it was proved even though after Riemann, after he discovered all I'm going to talk about, they needed his methods in order to prove this. But even though this guy looks pretty big, it still stays asymptotically bounded, and eventually the error goes to 0 as n goes to infinity. Eventually, this number, no matter how big this guy gets, and your errors will still get bigger and bigger, but this number compared to this number will go to 0. Just comments and consequences of the prime number theorem. This is the prime number theorem right here. Is the approximate probability that n is prime is 1 over the log of n. The nth prime number, and this is very interesting, the nth prime number is approximately n times the log of n. And which we'll see right now in the graph, n over log of n is actually an underestimate to the actual number of primes. Improved prime number theorem. Eventually, around 1838, how do you pronounce this guy's name? Dirichlet. Him and Gauss conjectured that the offset logarithmic integral, defined by this, the integral from 2 to x of 1 over log of t dt, actually improved on the original x over log of x approximation. And look at that 1 over log of t. Gauss is because he pretty much noticed this, that the approximate probability that n is prime is this. So it's from that he said, all right, let's graph the probability of all these primes and take the area under it. And surprise, surprise, it gave you a better estimate, like a much better estimate, as you will see. Here, just compare the numbers, and then compare, remember the 612 and this number, 10 to the 18, look how much better you did now, as the difference. They call it Lie of x, the logarithmic integral of x. So, another version of the prime number theorem is just this. This is just a better, so that concisely they can all be stated like this, that pi of x is about x log x, which is also about whatever logarithmic integral of x. All of these statements, they're all, it's a relation thing, so you can just, this guy is related to him, they're all related to each other. This is all now the improved prime number theorem, and you can see from the numbers why we call it the improved prime number theorem. It's a better estimate.
To be related means that the limit of the quotient.
Yes, exactly. Remember how I wrote that the limit, I can do pi of x over x log x, so log x over x. This approaches 1 the same way that the limit of Lie of x, and I can Lie of x over pi of x approaches 1, or I can do pi of x over Lie of x, that approaches 1. They all go to the same thing. So the improved prime number theorem. And this is the graph that I was telling you about. I had to photocopy this on my book. So here is the little step function, pi of x, pi of n. And then here's, I told you how x log of x is an underestimate. Here he goes. And then Lie of x, or it appears to be a little bit of an overestimate. How here, we're actually, I kind of messed up, we're actually more or less considering the absolute value of this, but you still get the point. It's just that this guy's a lot closer to the actual answer than x over log x. You can see it by this graph. And so we're trying to get here to this middle. We want exactly here. Alright, so enter Riemann now. In 1859, in his one and only paper on number theory, on the number of primes less than a given magnitude, Riemann set out to find the exact formula, the exact analytic formula for pi of x. In a little 8-page memoir, He revolutionized prime number theory, but not even overnight. It literally took about 30 years. People didn't even talk about this stuff. I mean, they probably talked about it, but not like a single paper was published for about 30 years. No real results. People were just, everything was too new. The methods, the ideas, everything was too new for everybody. So Riemann was way ahead of his time. So he set out to find this exact formula of pi of x. We are gonna more or less talk about that, but if I have time at the end, I'll go back to this exact formula because, if I have time, I'll get back to it. First, but before we can get more in depth into the study of prime numbers, to look for this pi of x, we need to introduce the Riemann zeta function. This is what we're all here to do, right? Well, what we're here to learn about. And then I like the choice of words, then we can unleash the methods of analytic number theory to study prime numbers. So the Riemann zeta function. That's how it is defined. Everybody here who took calculus 2, you guys remember just without this part, just this Dirichlet sum or whatever, without this part, Riemann just defined it, but without this part, you guys remember what this sum is. It's just the sum of the reciprocal powers. Remember from calculus 2, this guy converges if s is greater than 1. If s is equal to 1, then he's just harmonic series. He's just 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. And we know this diverges to infinity. So that's the pole of the zeta function. And the Riemann zeta function, so if s, or the real part of s, because later on we're going to start talking about complex numbers, if s is greater than 1, zeta is defined by this infinite sum, let's call it, right? And whatever, we know, so for s greater, the real part of s greater than 1, zeta's no problem, a calculus 2 student can compute them. We have the famous value of zeta of 2, which is the sum of the reciprocal squares. It's just 1 plus 1 over 4 plus 1 over 9 plus 1 over 16. And Euler, which happens to be zeta of 2. I'm just plugging in 2 right here and just getting the sum of the reciprocal squares. And Euler proved that this converges to pi squared over 6, which is pretty cool. Alright, before we can continue though, I need to show you guys, some of you may have seen this before, but what is zeta's connection to prime numbers? This is what we're here to talk about, prime numbers. What is this connection? And the connection is, it's characterized by the factorization of the zeta function called the Euler product formula. What's called, you can see it right here, it's just where this infinite sum is going to be expressed as an infinite product, where here n runs from 1 to infinity, here p runs all the prime numbers. And we're gonna prove this right now. So let me see actually. I'm gonna put the sub. Actually, I think I'll say this. So zeta of s, you said it's going to be n equals 1 to infinity, 1 over n to the s. So this is exactly what you see there, 1 plus 1 over 2 to the s, plus 1 over 3 to the s, So what we're going to do, I'm going to do the easy version of this proof. It's going to remind you of the little thing we've seen a little while ago. What I'm going to do is I'm going to multiply this whole guy by 1 over 2 to the s. So 1 over 2 to the s times zeta of s. Supposing that, let's say, we just suppose that real part of s is greater than 1, then zeta is absolutely convergent. So once we have absolute convergence, we can do whatever we want. We're going to multiply zeta times 1 over 2 to the s. And so 1 over 2 to the s times 1 is just 1 over 2 to the s. And basically, it's just going to double every number. 4, 6, plus dot, 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 right? And then what we're going to do, we're going to subtract this line from that line. So we're going to do zeta of s